Hi everyone, I'm Martin and I have been a software engineer at Espressif for over 2 years. In this talk I will briefly introduce file systems using Espressif chips, especially FAT file system and our recently implemented Python tools for generating and parsing FAT images on the host. This presentation will cover the properties of FATFS in Espressif microchips, alternative file systems, advantages, disadvantages, a brief look into the ware leveling layer, generating and parsing images on the host, a quick demo, and last but not least, questions and answers session. The FAT file system is a simple protocol developed in 1977. It is in use till the present, especially in small devices like microcontrollers. The original types of FAT file systems are FAT12, FAT16, and FAT32. FAT12 and FAT16 differ mainly in the number of clusters, and FAT32 has a richer structure that can contain more metadata than FAT12 and FAT16. According to specification, Microsoft originally developed it for IBM personal computers that used little-endian architecture. Because of that, the protocol also uses little-endian. As I already mentioned, the number of clusters implicitly determines the type. Documentation, however, allows redefining the default type. The basic building block is the FAT, File Allocation Table. It consists of one or more sectors, and every physical cluster matches a logical entry in the table. In other words, the file allocation table has a particular number of entries, and the block in the table corresponds to the physical cluster. The FAT type determines the size of the block in the table, such that FAT12 has 12 bits in one entry, FAT16 has 16 bits, and FAT32 has 32 bits. The file is allocated as a linked list of clusters with nodes stored in the file allocation table. The linked list node corresponds to the FAT table's entry. If the node is final, the entry is the highest possible number on the given number of bits. Therefore, all Fs in hexadecimal code or all ones in binary. All zeros determine free space. Otherwise, the number in the FAT entry refers to the address of the next cluster in the file chain. The clusters contain either the file content or references to the other files or directories and yield the tree structure. Another property of the FAT file system is the size of the names. You can choose between short and long file names by specifying the option in kconfig using idf.py menu config. Without selecting the long file names option, the protocol uses pattern 8.3 file names. Otherwise, you can use the universal coded character set UCS when long file names are allowed. The file system is not natively flash-friendly, and the official specification does not provide ware leveling. That is why Espressif implemented its ware leveling layer with adequate disk protection. The ware leveling algorithm is a non-standard aspect of our FAT file system and is the main problem in generating and parsing the FATFS image. But let's now talk about other file systems. The frequently used file system for embedded development is, for example, SPI-FFS or LittleFS, an improved descendant of SPI-FFS. There is not much support for the LittleFS yet, and SPI-FFS is officially deprecated and lacks a directory structure by design. You can still use our tools for generating SPI-FFS partition, either the Python free tool SPI-FFS gen.py or the C++ tool MK SPI FFS. So what would be the reason to use FAT file system? We provide where leveling, which is not native and ideal, but is definitely supported. The system has extensive cross-platform compatibility and is still a standard on many devices. Its essential feature is the ability to encrypt the partition, which is not supported, for example, on SPI FFS. A disadvantage is that FATFS is not flash-friendly since its origin and may not provide the best flash behavior. It may lead, for example, to non-deterministic or slow I/O operation times. Because it is quite a specific topic and the read-write mode requires it, I will briefly share some information and knowledge about the wear out and wear leveling. Flash wear out means overusing a particular physical block of the memory instead of balancing the load between all blocks. On the other hand, wear leveling is an algorithm trying to prevent wearing out and prolonging the disk's life. The main goal is to balance the usage of the sectors and avoid excessive use of some and no usage of other blocks. If you performed, for example, million write operation on the same file, it would erase the same set of blocks a million times. And that would speed up wearing the disk out. For example, if you have thousands of blocks, ideally implemented wear leveling can extend the disk's lifespan 1,000 times. The design of an algorithm assumes that the worst operation in terms of wear and tear is sector erase. It means changing binary 1 to binary 0. The partition is initially encapsulated into a few more sectors, storing the information about wear leveling. Initially, the first sector was the so-called dummy. When the sector is dummy, it means it rests and is not in use. At the end of the partition are placed sectors holding information about wear leveling configuration and its state. After every erase operation, we add a new 16 bytes record into the state sector, and the dummy sector is swapped with the following sector, or the first sector in case the dummy is the last. When the dummy sector reaches the maximal position, we erase the state sector records and increase the counter in the state sector. Notice that after the first round, the first sector is in the last position. When the first logical sector reaches the first position again, the counter placed in the state sector is then rewritten to 0. The main principle is to choose a different sector after every operation to rest and prevent overusing one specific memory block. Wear leveling is necessary for optimal run of the programs. However, it is the biggest issue in parsing and mounting images on the host. The position of the dummy sector has to be non-trivially determined based on the state sector. For initializing the wear leveling, we need to add all the crucial metadata. That's also the reason why we decided to provide a partition generator and partition parser. The community provided a couple of open source tools or Unix commands for packing the folder to the FATFS compatible binary image. However, the community implemented these tools in compilable languages without wear leveling support. Therefore, customers requested a Python tool similar to SPI-FFS gen.py without requiring compilation like the C or C++ tools. The partition generator that is served as a part of ESP-IDF is a Python free-based tool providing the complete functionality required for encoding local folder on the host into the binary FAT file system image. The tool can be used as a command line Python tool, or, even more convenient, using an integrated part of our build system as a CMake function that users must add to the project's cmakelists.txt file. The tool can generate images with already mentioned ware leveling, short or long file names, FAT12 and FAT16. Extending the functionality to FAT32 is an objective of the following work. After working with the FAT file system on the device, the user can download the partition binary image using part tool or ESP tool. The standard tools for mounting a file system on Unix systems, as mount or disk-util, don't support ware leveling and evaluate the partition extracted from the device as an invalid partition. ESP-IDF provides the reverse FAT file system generator tool to mitigate this issue. The script FATFS parse.py is a command line tool that takes as an argument the binary image and generates an equivalent folder on the host. The user needs to specify whether long names and ware leveling are supported. In the future, we plan to detect these properties automatically. To sum it up, the users can now generate and parse FAT images on the host. Current restrictions are FAT12 and FAT16 with ware leveling and long file name support. The command line tool or CMake function is used to encode the local folder into the binary image. To flash the partition into the device, you can use ESP tool. Decoding is possible only by command line tool. Extracting from the device can also be done by ESP tool or also a part tool. The following plans include support for deriving the minimal partition size for a given folder, detection of ware leveling and long file names, an option to have multiple FAT tables, a chance to forcibly redefine the FAT type to non-default type, FAT32, and anything that our user finds useful. Suppose you could think about any FAT-related feature or anything you wish to have in the ESP-IDF framework. In that case, we strongly encourage you to create a feature request in the Issues section in our GitHub repo. We will be also very happy for any feedback, bug report, or question on GitHub or the forum esp32.com. Now, let's do a short demo to propose a simple use case for FATFS gen.py. The example runs on the ESP32S2, but you can choose any ESP-IDF compatible product with sufficient memory. The demo will be a simple HTTP file server. The file server needs its file system, and we decided to use FAT. It is possible to format a new valid partition directly on the chip, or to flash the partition in advance and then mount it on the device. For that purpose, we use the CMake function in our project, which will involve generating the partition from the local folder and flashing it into the device. Users need to add a function below the component register. And now, as you can see, we already built, flashed, and now we are monitoring the device and program running into that device. Now, as we can see, the server is up and running on the given IP using port 80. We can now try to store a JPEG file from the local machine into the device using the web interface. And why don't we also try to upload a larger PDF file, MQTT white paper. This takes a little longer time to add to the device's FAT file system, but now it is already in there. And let's now perform a couple of delete operations. Let's delete hello.txt and also a content of sub folder, which is now empty, and we can delete it all. Let's now terminate the server and extract the partition out of the server. For extracting the partition, we are using the script extract, and we will take a look at this script now. For given script and for extracting the partition, we are using a partition table and generate the part tool that is also part of ESP-IDF framework. This script is not added to the system path using our sourcing script, so we have to do it manually in Python using the absolute path. Now we can conveniently import part tool target and partition name, which is a required functionality for extracting the partition out of the device. Part tool target takes as an argument the port that connects the device with our machine, and partition name is, in my case, storage. This can be verified in the partition table of the demo example, which is truly storage, and we can find there also some other essential information as the size of the partition and also the starting offset. The FATFS.img is the file that will contain the binary partition after extracting it from the device. Now the script terminated successfully, and we can verify if the desired file is already present in the computer, and it is. Now we would like to create a folder that contains the folder tree from the fatfs.img. For that purpose, we will use the fatfs.parse.py script. This script is also not in the system path, so we have to use the absolute path to access the script, and we also use the flags long name support and var leveling support because we use them also in our HTTP file server. We'll apply the script to the binary image extracted from the device fatfs.img. The script ran successfully, and now we can take a look at the content of the generated folder called Espressif. The folder contains the information and the files that we expected, including web page, index.html, also the icon required for Google Chrome, and the image that was referenced in the web page. Two files that we've added to the file system are present here as well, excluding the file that we removed earlier. And this is all from the demo, so thank you for your attention. And now I believe it is the time for questions and answers session.
Okay, we are back for one more Q&A, and for this Q&A, I will like to invite Martin and Roland. How are you guys?
Hi, Pedro. I'm great.
Yeah. No.
Hi again, okay. Pedro. I'm also great. How are you?
Yeah, I'm good. So,
can you hear me?
First question.
Oh, great.
Okay, so is FATFS gen.py also compatible with Python 2?
I'll take this question. No. FATFS gen.py is no longer compatible with Python 2, similarly as the whole ESP-IDF, so you can only use it with Python 3.
Okay. One more.
Yes. If I may add also that, yes, Martin mentioned that it is by IDF not supported, and therefore during the implementation, we haven't even considered to stay compatible with Python 2, since we knew that in the environment where it will be used, nobody will be actually using it. But I don't think there is any would be any significant
Okay.
like effort to make it compatible if it would be necessary.
I see. And how about like is FATFS gen.py integrated with IDF.py or ESP2.py?
I can take this one as well. Well, no, FATFS gen.py is not integrated with these two tools, so you can use it only as itself alone, as a command line script, or you can use a cmake function, which is integrated with the command line script.
Okay, so I have one more question. This is about
that means, sorry, that just explains a little bit more. It is integrated into the build system, so actually it's part of IDF.py build process, and for ESP tool is just like a transparent thing. It just will flash a fat partition, but it doesn't care about the generator itself.
Okay, so I will move to one more question. So this is regarding performance. So what the amount of performance penalty is caused by using FATFS generation and parsing?
Well, I've seen this question on YouTube, but I didn't really understood what does it mean, the penalty, by the Wojciech who asked the question. Roland, do you understand it?
Probably it is since the generation is takes place on the host side, so it more likely won't take any significant penalty on the runtime, and yeah, on the ESP where it should be critical, it's just a partition goes there. So.
Mm-hmm. Yeah, so basically no penalty.
But I think we have not considered the actual performance of the script yet. We haven't had any issues with that. So maybe in the future, if somebody would generate a very large file system images, then should get back to it and optimize it if it's.
Okay, and talking about the future, do you have anything to share, like any future planned roadmap that you can share with us?
Well, definitely, according to discussion with our storage team, we are planning to add support for FAT32, which is not a part of the FAT file system generator, and except for that, maybe to make it more compatible with the official documentation. What do you think, Roland?
Yeah, actually, the community could help us with this a lot. So if you like this feature and you would want something more from it, then don't hesitate to create a GitHub feature request for us. So we at least we get some feedback, know that people are using this tool, and there's something needs to be done, needs to be improved in this direction.
Good. Okay, so I'd like to thank you for the talk and to be here for the Q&A as well. Thank you, guys.
Thank you very much. Bye.
Thank you. Bye.
Okay, so the next talk is quite special. It's from an external company, Arduino, and Alessandro will talk about the news about the new IDE 2.2.0. And yeah, so let's hear what he has to say.